For this lesson, we're going to be investigating rational exponents. So if I'm investigating the meaning of a to the power of 1 over n, then if I took the square root of 5 times the square root of 5, that would be the same as the square root of 5 times 5, or 25, and the square root of 25 is just 5. If I took 5 to the power of 1/2 times 5 to the power of 1/2, 1/2 plus 1/2 is 2 over 2, or just 1, which would also equal 5. If I had the cube root of 2 times the cube root of 2 times the cube root of 2, that's the cube root of 2 times 2 times 2, or 8, and the cube root of 8 happens to be 2. If I have 2 to the power of 1/3 times 2 to the power of 1/3 times 2 to the power of 1/3, 1/3 plus 1/3 plus 1/3 is 3/3, or just 1. So what's the meaning of the 5 to the power of 1/2? It is the square root of 5. What's the meaning of 2 to the power of 1/3? It's the same as the cube root of 2. We know that they are equivalent. So if that's true, then I can convert a rational exponent into its radical form and then theoretically solve it. If I have 25 to the 1/2, that's the same as the square root of 25, which would be the same as 5. If I have 64 to the 1/3, that's the same as the cube root of 64, which is just 4. If I have 81 to the 1/4, that's the same as the fourth root of 81, which is 3. If I'm using variables, all I can do is just write the radical form. X to the 1/2 is the same as the square root of x. B to the 1/3 is the same as the cube root of b. P to the 1/10 is the same as the 10th root of p, and a to the 1 over n is the same as the nth root of a. Now, if I have a more complex ration where I have a numerator that is not 1, then if I took the square root of 5 to the power of 3 times the square root of 5 to the power of 3, that's the same as the square root of 5 to the power of 6, which is the same as the square root of, if I did 5 to the power of 6, that's going to be 15,625, which is the same as 125. If I had 5 to the 3 over 2 times 5 to the 3 over 2, then that would be 5 to the 3 over 2 plus 3 over 2. They have the same denominator, so I can just combine the numerators and get 6 over 2, which is the same as 5 to the power of 3. And 5 to the 3 is 125. I can see that they're equivalent. So what does 5 to the 3 over 2 mean? It's the same thing as the square root of 5 to the power of 3. If I'm doing the same process for example B, then if I had the cube root of 2 squared times the cube root of 2 squared times the cube root of 2 squared, that would be the same as the cube root of 2 to the power of 6, or the cube root of, in this case, if it's 2 to the power of 6, 64, which just gives me 4. If I said 2 to the 2 over 3 times 2 to the 2 over 3 times 2 to the 2 over 3, then that would be 2 over 3 plus 2 over 3 plus 2 over 3, which would be the same as 6 over 3, or just 2, which would equal 4. And once again, I see my results are the same. So 2 to the power of 2 over 3 is the same as the cube root of 2 squared. So if I apply that with the variables, then I could say that x to the 5 over 3 would be the same as the denominator becomes my index, and the numerator stays my exponent. For example 2, I'm going to have the fifth root of b to the power of 4. For example 3, I have the square root of p to the 5. And for example 4, I have the n root of a to the power of m. So, if I'm evaluating these values, then I could say that a to the 2 over 3 is the same as a to the 1 over 3 squared, which is the same as the cube root of a squared. The cube root of a is 2, and when I square it, I get 4. If I said that a to the 2 over 3 is the same as a squared, then to the power of 1 over 3, then I could square a and then take the cube root of it. A squared is 64, and the cube root of that is 4. Now when it says which of the above is easier for evaluating 8 to the power of 2 over 3, it's entirely a personal preference, but typically, like with most cases in math, 1 is going to be considered easier because it's easier to make numbers smaller and then expand them out than it is to make numbers bigger and then try and shrink them back down again, especially if we're just doing it with mental math. So if I'm doing that for this case, I might not know what 64 cubed is, but I know what the square root of 64 is, so I'm going to say that it's going to be the square root of 64, and then cube that. If the square root of 64 is 8, and I'm going to cube it, then that is the same as 8 times 8 times 8, or 512. For example 2, I might not know what 4 to the power of 5 is, but I know that the square root of 4 is equal to 2, and then I can do 2 times 2 times 2 times 2 times 2 times 2, which would give me 32. For example 3, I definitely don't know in my head what 81 cubed is, but the fourth root of 81 I know is 3, and 3 cubed is going to give me 27. Now, if I have a negative rational exponent, if I'm using the exponent laws to simplify 8 to the power of 2 over 3 times 8 to the power of negative 2 over 3, then that would be the same as 8 to the 2 over 3 plus negative 2 over 3, which is going to cancel out to give me 8 to the 0, or just 1. If I'm canceling out and wind up with 1, then if I took a to the negative 2 over 3 and wrote it with a positive exponent, then that would be the same as 1 over a to the 2 over 3. And I'm going to move the base, or the power, down to the denominator to make the exponent positive again. And then I can do the same process that we were doing in the previous examples. If I have 1 over the cube root of 8 squared, then that's the same as 1 over 2 squared, or just 1 over 4. So if we're breaking down the rules for rational exponents, we know that the denominator becomes my index of the radical, my numerator stays an exponent. I can either make it smaller and then apply an exponent to make it bigger, or I can make it bigger using the exponent in the numerator and then use the radical to make it smaller. There isn't a right or wrong way to do this. It's just whatever you find easier. Most people tend to do the first. Make it smaller, then make it bigger. If n is even, then a has to be a non-negative because I can't take a square root, a fourth root, an eighth root, a sixth root of a negative number. It will not work. When I go to my negative ones, all I do is first I move it into the denominator, and then I do the exact same process I would have done if it was not in the denominator. I'm going to either take the nth root and then apply it to the power of m, or I'm going to apply it to the power of m and then take the nth root. And in this case, if n is even, a still must be positive in order to actually solve it. Can't take the nth root of a negative.